Welcome to this quick tutorial on how to determine the temperature compensation parameters for the Sen 6X Star engine, the built-in temperature and humidity compensation algorithm. Since humidity compensation is automatically done internally by the engine, we only have to determine the parameters for the temperature compensation. By following these steps, you'll unlock the full performance potential of the Sen 6X and achieve highly accurate measurements. This video complements a more detailed written guide, which you can access via the QR code shown below. To calibrate the Sen 6X sensor accurately, you need to determine several key parameters. These are then processed by the sensor's internal engine to compensate for any temperature and humidity influences caused by your device. We will first walk through a basic calibration that requires only a single location and delivers reliable results for most applications. For those seeking even greater precision, we'll outline a more advanced calibration method that uses two separate locations, enabling accurate calibration across a broader temperature range and faster device response to temperature changes. Throughout this video, we will refer to these approaches as the basic parameter identification and the advanced parameter identification, respectively. It's essential to do the calibration in an environment with stable conditions, such as a climate chamber. If no climate chamber is available, you can also use a cellar, as they tend to offer stable conditions. Make sure the location you choose does not have air conditioning, as it can significantly destabilize the environment. For the advanced method, you will need two of those environments, and one of the locations should be approximately 10 degrees warmer than the other one. For the calibration, you will also need two Sen 6X sensors, at least one SHT4X reference sensor, an SEK sensor bridge, three connection cables, a laptop, and of course the device that will integrate the Sen 6X. First, connect the white cable that has an Ethernet end to the Sen 6X. Then insert this Sen 6X directly to your device. Place the device as far away as possible from any objects or walls. Connect the second Sen 6X directly to the electronic plugs of your device. This second Sen 6X is required to ensure the device operates normally and behaves as it would in the field. Then place the SHT4X reference sensor at a suitable distance away from the device, ideally between 20 centimeters to 50 centimeters, and at least 5 centimeters away from any wall. Ensure it is positioned so that it is not exposed to direct device-generated airflow. Then connect the cables to the sensor bridge. You can also use more than one SHT4X reference sensor, which not only increases accuracy, but also helps verify the stability of the calibration setup. Finally, connect the sensor bridge to your laptop and position the laptop as far away as possible from the device. Next, you need to prepare the software for the calibration. To begin, download Control Center from the Sensirion website. Once the download is complete, open the application. You should see both the Sen 6X and SHT4X sensors listed in the program. With that, you're all set for the calibration. To begin the calibration process, first power down all electronics in the environment, including the Sen 6X and the sensor bridge. This step is essential to allow the entire setup to acclimate properly. Leave the system undisturbed for at least 3 hours. After this period, return and power on the device. In Control Center, click the gear icon next to the Sen 6X to open its settings. In the Settings menu, locate the option Enable Raw Values Plots, select it, and click Done to save. A new plot should pop up on the bottom right of the screen. Move it to a desirable position. Now you can press on the Start Measurement button. Do all those steps as fast as possible and ensure that your laptop will now stay on for the whole procedure. During the first few seconds, check that the raw temperature readings of the Sen 6X, which can be found here at the bottom, and the temperature readings of the SHT4X sensor, found in the temperature plot above, do not differ by more than 0.5 degrees Celsius. If the discrepancy exceeds this threshold, the acclimatization period was insufficient. In that case, power off the setup again by unplugging all devices, wait an additional 2 hours, and then repeat the check. Once the temperature curves align and show minimal deviation, you're ready to proceed. Allow the device to heat up naturally. The Sen 6X temperature will gradually increase. which can be seen here at the bottom as the device heats up. If the signal has fully settled and remains unchanged for around 30 minutes, or at least for a meaningful period longer than just 1 minute, you can move forward. If you're using a single environment for the parameter identification, you may now stop the measurement and extract the calibration parameters in the next step using the collected data. This is explained at minute 6. If you're using the advanced parameter identification setup, additional steps will follow now, so don't stop just yet. Now, you will move to the second environment. Carefully transfer the entire setup from the first environment to the second, which should be approximately 10 degrees Celsius warmer. Leave everything plugged in for this transfer. After the transfer, wait at least 3 hours until the equilibrium of the SENS 6X temperature curve has been reached. When the temperature signal has fully stabilized, you can stop the measurement. Now that you have collected all the necessary data, it is time to extract the parameters required for compensation. Start by opening Data Viewer in Control Center. You should see the data you've previously acquired. Otherwise, you can add it by pressing on the plus on the bottom. In this example, the data was obtained using the Advanced Parameter Identification method with 2 environments. However, we also explain in the following how the parameters can be extracted using the Basic Parameter Identification method. Navigate to the Temperature tab and locate the plot showing the temperature readings. You should see 2 curves with 2 slopes in 2 constant regions in the bottom left plot if you followed the Advanced Parameter Identification method. If you use the Basic Parameter Identification method, you should see only 1 slope in 1 constant region. Next, go to the Algorithm tab on the left-hand side and click the plus symbol to add a new temperature algorithm. You'll now see several empty fields for parameter input. The first 4 parameters you'll need are T1, T2, K, and P. These values depend on the size of your device. We provide 3 predefined parameter sets. For small devices, so for example, indoor air quality monitors, use the top row. For large devices like air purifiers, use the bottom row. For anything in between, refer to the middle row. After inserting the appropriate set, click Save. A new red dotted curve, which is quite similar to the old one, but accelerated, will appear in the plot. This new curve will now be used to determine the remaining parameters needed for the compensation. The first parameter that you can now determine is the offset. If you perform basic parameter identification using a single environment, the offset can be directly calculated by reading off the difference between the green SHT4X reference temperature and the red dotted SENS 6X temperature curve. We inserted the values from the example curves into the formula for reference. As you can see, the offset will likely be negative, as the device tends to overheat. If you followed the Advanced Parameter Identification method, using 2 environments, the offset parameter is defined differently. You'll first need to determine the individual offsets for each chamber. Then with those offsets determined, calculate the offset parameter using the following formula. It incorporates a slope parameter, defined as shown here. To make things clearer, we've included the values from our example data. Since the device typically exhibits a slight over-temperature compared to ambient conditions, the offset parameter should be negative. The slope parameter can be either negative or positive and is typically less than 0.1, depending on the data. Once calculated, enter the offset parameter in the section called Slot 0 into the corresponding field. If you're using the advanced method, be sure to also enter the slope value defined before. Only 1 parameter remains, the time constant, called tau 63. This represents the time it takes for the device to reach 63% of the final stabilized temperature. To determine tau 63, first calculate 63% of the final temperature using the formula shown here. Again, we've inserted example values to guide you. Next, take a close look at the temperature curve. Identify the point where 63% of the final temperature is reached. Now find the exact time at which this temperature is reached. The duration from the start of the measurement to this point is your tau 63 parameter in seconds. You can then enter the parameter in Data Viewer in the field called Time Constant. After pressing Update, the updated red dotted curve should now closely align with the green reference. Especially as soon as equilibrium is reached, If something is still wrong, or if you're just curious about what each parameter represents and why there are multiple slots to insert parameters, consult the paper guide for more insights. All parameters you obtained earlier can now be added to Control Center and sent directly to your sensor. To do this, open the sensor settings and navigate to the RHT tab, where you can input all relevant values. Once configured, starting a new measurement should result in the SEN6X temperature curve, aligning closely with the SHT4X reference temperature curve most of the time. Keep in mind that these parameters are stored in volatile memory in the SEN6X, meaning they will be lost after a power cycle. To preserve calibration, you'll need to transmit them to your final device via I2C each time the system powers on. It is important to transmit them within the first few seconds of startup, not afterwards, as otherwise the time constant becomes misaligned. For more details on this process, refer to the paper guide. That's all. If you notice any unusual or unstable behavior during operation, please refer to the printed guide. It additionally includes detailed instructions on configuring multi-mode compensation, allowing you to use multiple parameter slots for different operating modes of your device. The QR code to the guide is shown here,